Lead off this afternoon. It's my pleasure to introduce John Baldwin, who's telling us about Stein fillings and SE2 representations.
All right, well, thanks a lot for the invitation. Josh asked me to remind Gordona to remember to thank the organizers at the end of her talk. There you go, Gordona. Everything I'm talking about today is joint with Steven. Apologies to everyone who's seen this talk before. To avoid redundancy, I thought I'd just leave out all the jokes. So this will be a very serious talk. And any serious talk in low-dimensional topology should start with Perelman's theorem, I've been told. So if Y is not the three-sphere, then the fundamental group of Y is not trivial. And unless otherwise specified, all three manifolds will be closed, oriented, connected, etc. So, well, this tells us something about the fundamental group of three manifolds. What else do we know? What other kinds of questions can we ask? What groups can be the fundamental groups of three manifolds? And I thought I'd start with a nice, fun example. So, for example, a fundamental group of a three manifold can't be z to the n or n not equal to 1 or 3. And probably a lot of you have seen this, but I thought it was a nice exercise. So just to amuse myself, we'll go through it. What's that? Oh, yeah. Thank you. Yes. All right. So suppose so. Well, then, since it's not a free product, this implies that Y is irreducible. And because it's not S1 times S2. And so this implies that pi 2 of Y is equal to 0 by the sphere theorem of Papakyriakopoulos. So if we look at the universal cover, so the universal cover then, well, it has pi 1 equals 0, pi 2 equals 0, and it's non-compact, since the fundamental group is infinite here, and so it's contractible. By the Hurewitz and Whitehead theorems. So that means that Y is homotopy equivalent to a k pi 1, k zn1. Right? So in particular, the n torus. And if Y is a closed three manifold, that can't happen unless n is equal to 3. So that's the proof of that. So that's something, but how do we study three manifold groups more generally? Well, one way to do that is to study representations, so homomorphisms from the fundamental group to some other group. And that's what we'll talk about in this talk. And in this talk, G will be, we'll focus on the case G is equal to SU2. And one of the most basic questions you can ask is whether there always exists a non-trivial homomorphism when Y is not the three-sphere. So I'll write this as a conjecture. This appears as a problem on Kirby's list. So if Y is not the three-sphere, then there always exists a non-trivial SU2 representation. Okay. And that's sort of the motivating conjecture for the rest of the talk. I should mention recent work of Zentner from last year. Who showed that this is true, this holds for SL2C in place of SU2. And the thing about SL2C is that you know that if you're a hyperbolic 3-manifold, then you automatically admit a non-trivial SL2C rep. So that sort of kills the most difficult cases. But the problem appears to be significantly harder for SU2. All right. So I should say that we only have to worry about, we can assume that Y is a homology sphere. So otherwise, you can always find a non-trivial representation by factoring through the first homology. So if you like, into U1 contained in SU2. Okay. So whenever we're asking about the existence of non-trivial representations, the assumption will be that Y is an integer homology sphere. So the goal of this work was to provide a new connection between contact geometry and these SU2 representations. And this connection is going to come via instanton Floer homology. But I'll postpone that for just a second. I want to first maybe give some of the contact geometric background and state a theorem. And I think this Gordon might benefit, so it's not a complete waste of time. So what is the contact geometric information that we're dealing with? Well, first, let me tell you what a contact structure is. Probably a lot of you know. This is just a quick reminder. So a contact structure on Y is a two-plane field. Xi on Y, which is totally non-integrable. So one way to formulate that concisely is to say that we can realize this two-plane field as the kernel of some one form which satisfies alpha wedge d alpha is not 0, and the convention is greater than 0. And so that what this is a family of two planes, and what this condition ensures is that you can't ever find a surface in your 3-manifold whose tangent planes agree with the contact planes, even in some small neighborhood. All right, so in the standard example is what's called the standard contact structure on S3, or R3, given as the kernel of dx plus y dz. So if you imagine the blackboard as the xz plane and the y-axis coming out this way, what happens is the contact planes rotate as you move in maybe the negative y direction. Well, either direction, but they rotate in this way maybe as you move in the negative y direction. All right. So those are contact structures. These are objects on 3-manifolds, and the corresponding 4-dimensional object that I want to talk about today are what are called Stein fillings. So let me just at least write down the definition of a Stein manifold, or the way I want to think about it. So a Stein manifold you can think about as just a complex submanifold of projective space, if you like. But for us, it'll be a 4-manifold, smooth 4-manifold, together with an integrable, almost complex structure. Together with an exhausting, proper, strictly pluri-subharmonic function, which is to say, with a function phi from x to r, such that, well, if we can define a 2 form, minus d decomposed with j, and the condition is that this defines a metric, a Riemannian metric, by GVW is equal to omega VJW. Okay, so that's the condition on this function. So suppose we have this, and C is a regular value. Phi. So then the preimage is a smooth three-manifold. We just call it Y for simplicity. And it bounds the preimage of, well, minus infinity to C. So we'll be assuming, as part of the definition, that this is compact. And the condition here, that this defines a metric, ensures that if we look at the space of complex lines on T, on Y, this is a context structure on Y. So whenever you have a setup like this with the, and so we'll call this compact thing a Stein domain bounded by Y. So whenever Y is the boundary of a Stein domain in this way, you get a naturally induced context structure on Y. And you know, the typical example is the S3 as the boundary of unit ball in C2, where phi is the radial function. So this gives rise to a context structure on S3, and actually up to, well, compactifying R3, it agrees with this one. Okay. So then now I can state the first main theorem, depending on time, the only main theorem. So, and I'll write it here so as not to erase it. So the theorem is that if Y bounds a Stein domain, Wj, that's not an integer homology ball. Then Y admits a non-trivial SU2 rep. Okay. And as I hope to convey, this is actually somewhat useful for showing that three manifolds admit non-trivial SU2 representations. Yeah, I mean, that's part of, I want that to be part of the definition here, yeah. Okay, so we'll use this as a tool in some examples to show that things admit non-trivial SU2 representations.
Sorry, okay, so you said W is compact here?
Yeah, I want W to become, I mean, that's part of the definition of the function. Yes, I'm requiring that these be compact. Yeah, it's proper. It's a proper exhausting Floer subharmonic. Okay. Oh, you can think of, there's a nice topological way of thinking about these Stein manifolds. They're all built from the four ball by attaching 1 and 2 handles, four-dimensional 1 and 2 handles. And the 2 handles are attached, in particular, along Legendrian knots in the boundary. Legendrian knots are knots which are tangent to the contact planes. And if you attach these 2 handles with framing -1 with respect to the natural framing by contact planes, it turns out that you can extend the Stein structure to the result of attaching the two handles. So that fact will come up later as well. All right. So I'd like to give sort of, I don't know how to describe it, amusing corollary of the main result. Which is a proof of a much weaker result than is already known. So the corollary is that any Stein domain with contractible boundary is contractible. So let's call this W. Forget about the Stein structure, J, for a moment. And let's say that the boundary is Y. So what's the proof? Well, the proof is pi 1 of Y is trivial. So no non-trivial SU2 reps. And by the main theorem, that implies that this W is an integer homology ball. Oops.
Is it an assumption on the boundary of the domain that it's contractible, or that's simply connected?
Yeah, sorry. I just, that, yeah. Well, yeah, sorry. Yeah, simply connected. Thanks. It's definitely not contractible. Okay. Right, so W is an integer homology ball. And in general, you know, if you have a three-manifold bounding a Stein domain, then you know that pi 1 of the three-manifold surjects onto pi 1 of the Stein domain. This is a general fact, and it follows from what I said before. Every Stein domain is built from a four-ball by attaching 1 and 2 handles. And so you can, in reverse, build that from the three-manifold by thickening it up, attaching 2 and 3 handles, and then a four-ball. So you're not attaching any one handles. So that explains the surjection. So that implies that this is equal to 0. And then again, an application of well, this has the W also has no third homology because again, it's gotten from the four ball by attaching 1 and 2 handles. So an application of Hurewicz plus Whitehead finishes the proof. It's contractible. Of course, this also follows from some fairly well-known results of Perelman and Eliashberg. So if your manifold is simply connected, then as we saw, you're the three-sphere. And the only Stein filling of the three-sphere is the four-ball. So that's an alternative proof. But at least this doesn't, you don't need Ricci flow or holomorphic curves for this. Okay.
Can you give an alternative proof of
No, yeah. Not yet, not yet. Okay, so as I said, it's also this result is also useful in proving the existence of non-trivial SU2 reps. So maybe, what are some cases in which non-trivial representations are known to exist? Well, when the Casson invariant is non-zero. When Y is Seifert fibered, or more generally, so this was a result of Finta, Schill, and Stern. So more generally, when Y is the twofold branch cover, so the branch double cover of S3 along a non-trivial knot. Just put it this way. And that follows from an observation of Sivek, Cornwell, and Ing, and Zentner, but primarily from hard work of Kronheimer and Marufka. Okay. Also, let's see, when your Y is surgery on a non-trivial knot, that's the result of Kronheimer and Marufka. And I'll start calling KM. And maybe lastly, when set up for Jen Hom. When Y is
Editing that out.
what's that? Oh,
We're editing that
she doesn't mind. Admits a symplectic filling. A weak symplectic filling with B2 plus greater than 1, greater than or equal to 1. Okay. So that's sort of a survey of when non-trivial reps are known to exist. One thing that the main theorem allows us to do pretty easily is reprove. Yeah.
So this surgery on non-trivial knots, did they prove one surgery
Yeah.
or 1 over n?
1 over n.
1 over.
Yeah. So for Fintuschel-Stern result, Fintuschel and Stern's result, well, I'll sort of give the idea of how we reprove their result in an example. So here's an example. So Y is the separate fibered space with base sphere. Given in this notation. So here's the surgery diagram. -2, 3 halves, -3 halves, -11 ninths. And the idea is that you can use this you can turn this into a Kirby diagram for a Stein filling of the boundary by just turning these components into Legendrians and then doing this contact -1 framing that I described, contact -1 framed handle attachment that I described before. So here's the Legendrian diagram. Okay, so each of these is a Legendrian unknot. And if you do TB -1 framing, then you see what you're doing is equivalent to this surgery. So this can be thought of as a Kirby diagram for a Stein form manifold. And, well, you've attached a bunch of 2 handles. So you're not an integer homology ball. Right? So that tells you immediately that the boundary admits a non-trivial SU2 representation. And you can handle all ciphered fibered spaces in this way. So I won't write it down as a theorem, but we also have examples where we can use this to prove the existence of non-trivial representations when these other things aren't so useful. So there are examples where the Casson invariant is 0, where Y doesn't have any symmetries. So in particular, it's not a branch to cover. When it's not obviously surgery on a knot, and when we can't find any sort of symplectic filling with this property. Okay, so I should give you some idea of where this theorem comes from. And as I said before, it comes from Floer homology. And specifically from some invariants of context structures that Stephen and I, over the years, have been defining in these different Floer homology theories. So let me just provide the briefest of outlines, which hopefully will give you some insight to what we're doing. So the main theorem is proven using context invariants that we define in instanton Floer homology. Okay. So the instanton Floer homology theory I'll be talking about is the sutured instanton Floer homology theory developed by Cronheimer and Mruvka. So we talked about sutured manifolds on a previous day of the conference. And what Cronheimer and Mruvka showed how to do was to associate to such a thing a group. And we'll be considering only a very simple sutured manifold. So given a closed manifold Y, we'll let Y of 1 denote the result of removing a 3-ball from Y and putting a single curve on the resulting boundary. So here's what it looks like. Here's the 3-ball, here's the outside, and this S1 is the suture. So this is a very simple sutured manifold. But the way Cronheimer and Mruvka's Floer homology theory goes in general is you have your sutured manifolds, this manifold with boundary and sutures, and the idea is to embed it in some closed manifold where instanton Floer homology can actually be defined. And for this, what we do is, for the simple one, the idea is to embed it into what I'll call Y bar, which is just what you can think of as the connected sum of Y with R times S1, so a surface bundle. So this is just some surface. And I think I like the following picture, which I learned from Steven Sivek. So here's Y. I've connected summed with R times S1, which I'll represent in this way. And okay, so we have a closed manifold, and let's pick some arc alpha, and to this we can associate an instanton Floer group. So we choose some, roughly speaking, we choose some bundle over this closed manifold with first Chern class Poincare dual to alpha. And this data allows us to define a group, the instanton Floer homology of Y bar, which is roughly the Morse homology of Chern-Simons functional on some associated space of connections of this bundle. So mod gauge transformations, certain gauge transformations. And often the problem in constructing instanton Floer homology is that when you pick this quotient, you don't get nice spaces because of the existence of reducibles, but the way in which this is constructed sort of circumvents those issues. So in this way, you get a group, and then the thing that you associate to the sutured manifold, the original sutured manifold, is a summand, some direct summand certain summand, which I'll denote, which is specified by this surface R in this group. Oops. Okay. So that's just sort of the schematic of the construction of this Floer homology. You form this closed manifold, and you look at a certain summand associated with this sort of distinguished surface that you have in the closed manifold. And Kramer and Rivka proved that, well, in fact, you can take sort of any surface bundle over the circle. The gluing map doesn't have to be the identity, and also the result doesn't depend on the genus of the surface, up to isomorphism. Okay. And then Stephen and I refined that a bit and showed that the various ways of constructing this group are related by canonical isomorphisms. And the advantage of that is that it allows you to talk sensibly about elements in these groups. And that's important for us, and what I'll say in just a second. But maybe first, let me tell you a bit more about what this has to do with SU2 representations, or tell you something a little bit more precise. So this theory, it turns out, is isomorphic by Kronheimer and Rivka to another instanton Floer theory. So they define something called singular instanton knot homology. So given a knot and a three manifold, they have some other way of defining an instanton Floer group. And so if you take the closed manifold and remove a ball, then the suture Floer homology of that is the same as the singular instanton homology of Y with the unknot. This group was more directly what they used to show that Kovanov homology detects the unknot. And these isomorphisms were also important in that work. So we can think of this as just an invariant of the three manifold. So at the risk of adding more notation, we'll just denote this by I sharp of Y. It's essentially a three manifold invariant. Okay. And it's sort of more transparent how this group is related to representations of the fundamental group. So you can show, for example, that this is defined, again, as the Morse homology of some trans-Simons functional whose critical set, well, corresponds to flat connections. And in fact, you can identify that with, so it's naturally identified with homomorphisms into SU2. Okay. So that's where the connection between this instanton Floer groups and homomorphisms into SU2 becomes really precise and concrete. And so in particular, if no non-trivial, if there are no non-trivial representations, then this consists just of the trivial homomorphism, which is always a non-degenerate critical point, and that implies that this group has rank 1. And this is defined over the complex numbers. Okay. So the brief outline will be to show that if Y bounds a Stein domain that's not an integer homology ball, then this group has to have rank bigger than 1, and that'll imply the existence of a non-trivial SU2 representation. That's the strategy. All right. So we need to make the connection somehow between Stein fillings and this group. And that comes by way of contact invariance. I should say that there's no real known relationship between this and sutured Heegaard-Floer homology, or Heegaard-Floer homology for closed three manifolds, but they're, I think, conjectured to be isomorphic after tensioning with C or something like that. Okay, so given a context structure, on Y, Sivek and I defined an assignment which associates to such a thing elements, an element, which we call C, following Heegaard-Floer homology, and it lives in the group associated to Y minus a ball, really with reversed orientation, but that's not so important. So if you're familiar with Heegaard-Floer homology, this looks a lot like what you see there, and in fact it enjoys some of the same properties. So for instance, we proved initially that if this invariant is 0 when C is over twisted. So I didn't talk about what that means, and I won't have need for it, so I won't say more about it. And it's non-zero when the context structure is Stein fillable. So when it arises as a space of complex lines in the boundary of a Stein domain, as I described before. All right, so then the main technical theorem we prove is the following, and it's a bit of a mouthful, so bear with me a little bit. So suppose W4 admits Stein structures, let's say J1 through Jn, whose Chern classes, whose first Chern classes are distinct. Okay. So that's the important condition on these Stein structures. And so each of these induces a context structure on the boundary. So let C sub I be the induced context structure on Y, which is the boundary of W. So then what we show this is bad board technique. And what we show is that the contact invariants associated to these context structures are all linearly independent. In this group. So in particular, this group has rank at least n dimension. Okay. So I should say that this is this is the analog of a theorem due to Plamenevskaya that she proved in Heegaard-Floer homology in reference to the Heegaard-Floer contact invariance. So you have a four manifold. It emits n Stein structures with different Chern classes. Then the induced context structures have linearly independent contact invariants in the group associated to Y. Okay. So then that's, well, that plus a little bit extra is enough to prove the main theorem. So let's just skipping some details, see, a lot of details, see how this follows. So proof of main theorem. And the details that I'll skip are how I can reduce to a simple case. So we can use a work of others so including Liska, Matic, and Freushoff, in particular his H invariant, to reduce to the case so to reduce to the case that this J here has non-zero Turing class. And then if J has non-zero Turing class, this implies that, well, once we have J, we have another Stein structure by looking at its conjugate. And the fact that this is non-zero implies that the Turing class of J is not equal to the Turing class of the conjugate. So now I have two Stein structures on this four-manifold W whose Turing classes don't agree. And that tells me that the dimension of SHI is at least 2 by the main technical theorem.
You need 2 times C1.
Yeah, there's no torsion in H2 either, so you need that. Okay, right. So the rank is at least, the dimension is at least 2, and then by the relationship with SU2 representations, we know that there has to exist a non-trivial representation. So, I mean, it's also interesting to ask about SU2 representations of rational homology 3 spheres. The question there, so as I mentioned earlier, if you're not an integer homology 3 sphere, you automatically admit a non-trivial SU2 representation. So for rational homology 3 spheres, the interesting question isn't about non-trivial SU2 representations, it's about irreducible SU2 representations. So the analog of the conjecture I wrote down at the beginning would be that every rational homology 3 sphere, that's not S3, let's say, admits an irreducible representation. But of course, that isn't true. Think about length spaces. So for rational homology 3 spheres, it's a hard problem to determine whether they admit irreducible SU2 reps. And for SU2, you can think about this as being the same as non-abelian. So representations that don't factor through first homology. And as I said, you know, for example, well, length spaces have abelian fundamental groups. So length spaces don't admit any. They don't admit irreducibles. And the problem of deciding when things do is still pretty open. So maybe, where's the thing? Right. So maybe a good initial place to to think about this question is for surgeries on knots in the 3 sphere. And even then, there's not a whole lot that we know. So Kronheimer-Mrivka proved, for example, that R surgery on a non-trivial knot admits an irreducible SU2 representation when the absolute value of R is less than or equal to 2. And I think it's still an open question about as to whether we get irreducible representations for R equals 3 and 4. That's not known. So for R equals 5, it's not true, right? Because 5 surgery on the trefoil is a length space. It doesn't admit
So is R integral here? Or?
Yeah, the question I think they asked was for R equals 3 and 4. I mean, even that, for that, we don't know.
The statement of the theorem is for.
The statement of the theorem is, yeah, for rational surgeries.
So are there any examples that you know don't have SU2 representations that are not so, that is not so for trivial reasons?
Yes.
Yes.
There are even hyperbolic manifolds that don't have
Yeah.
any.
Surgeries on the pretzel knot, right? Yeah.
Some random examples.
Yeah. So Lin was able to answer this when K is amplichiral. So we can answer the question also in some slightly different cases. So for example, one thing we show is that if the maximal self-linking number of a knot is greater than or equal to 0, so then there exists an irreducible representation for P over Q surgery on the K. For P over Q, I think it's less than 0, by convention reasons, whenever funny condition, no 0 of the Alexander polynomial evaluated at t squared is a root of unity. Okay. And so in particular, I should say P over Q equals 3 or 4 is fine. So the maximal self-linking number, maybe I won't describe that, but I'll say that some examples, some things which satisfy this are strongly quasi-positive knots.
So P over Q is negative.
Say what?
P over Q is negative 3 of negative.
Yeah, negative 3 or 4. Right. So I could also state the theorem for the mirror of K. Okay. Strongly quasi-positive knots, like Steve talked about. And the idea is again to use the main technical theorem to show in this case so the idea behind the proof, the fact that the self-linking number of K is greater than 0 turns out allows you to show to construct for any let's say negative n, where n is a positive integer. A 4-manifold, so a 4-manifold W bounded by negative n surgery, but supporting n Stein structures, sorry, n plus 1 Stein structures with distinct Chern classes. Okay. So I can describe how that works after the talk to anyone who's interested. But what this tells you by the main technical theorem is that the dimension of this group of the surgery, minus n surgery at least, is greater than or equal to, well, once I remove a ball, greater than or equal to n plus 1. So you can think about this as saying that so at least this is what we have for integer surgeries, and an exact triangle argument, or a bunch of them, implies that this group for P over Q surgery has dimension greater than or equal to P plus 1. Right. So we have this 3-manifold whose first homology has order P, but the rank of its Floer homology has dimension at least P plus 1. So one way to think about this is that, well, if we were in Hegardt-Floer homology, we would say that this is not an L space. Floer homology has dimensions strictly bigger than the order of its first homology. So we might say this is not an instanton L space. And it turns out that assuming that the reducibles, so the reducible SU2 reps are non-degenerate as critical points of the Chern-Simons functional, this implies that we must have an irreducible. So the sort of theme is that whenever you're not an instanton L space, there should be irreducibles. Now that's not true in general. You need a non-degeneracy assumption on, well, a Morse-Bott non-degeneracy assumption on the space of reducibles. And that, in this case, that non-degeneracy assumption is what's guaranteed by this condition on the Alexander polynomial. So this condition guarantees non-degeneracy of the reducibles. Okay. So there are other things along those lines that you can prove, but maybe I'll just stop there.
All right, questions for John?
I told you there'd be no jokes.
Thanks, John, again. And we'll resume at 3.